Hi guys, today we're going to go over Chapter 5, Section 3 for Honors Chemistry, Periodic Properties of the Elements. Valence electrons are the electrons in the outermost energy level of an atom. You can find the number of valence electrons by looking at the group number, or the group number minus 10 on the periodic table. For example, if I go down to this periodic table down here, the group number is at the top, and that tells us how many valence electrons are in that group. Group 1 has 1 valence electron, so all of these alkali metals have 1 valence electron. Group 2, the alkaline earth metals, all have 2 valence electrons. We usually skip over these transition metals for honors chemistry. Don't worry about them yet. We can worry about them in AP Chem. Group 13 has 3 valence electrons, and then group 14 has 4. Group 15 has 5 valence electrons, 16 has 6. The halogens, group 17, have 7 valence electrons, and all the noble gases, except helium, have 8 valence electrons. Helium only holds 2 electrons, so it only has 2. So it's an exception in the 18 group. All right, the octet rule says that elements in the S and the P blocks are more stable, which means they have lower potential energy, so their energy goes down when all of the S and the P orbitals are filled. So here is my S block over here. Okay, so all of these are the S elements. That's our S block. It includes hydrogen and helium over here. And the P block is this section over here. This is our P block. P block. These are all filling up P orbitals. The S block is filling up the S orbitals. Let's make this darker. Okay, so the S block is the first 2 groups, and the P block is these 6 groups over here on the right. When all of these orbitals are filled, it has lower energy, and the ones that have a full octet are going to be these noble gases right here. So this little section, group 18, these have completely filled S and P orbitals, so they are more stable, they're lower in energy, and all the other elements in the S and the P block want to be like the noble gases. That's why they're noble. They're the snooty gases. Okay, the octet rule applies again only to the S and the P block. We don't worry about the D block. That would be this center one right here. We don't worry about the D block or the F block until AP Chemistry. Okay, so this F block and D block we will worry about later. The S and the P block want to have 8 electrons. Coulomb's law is the reasoning behind all of our trends that we're going to see below. So Coulomb's law says that the force, that's what F is K, which we will not worry about. So we're going to completely ignore K, times Q1. I'll write this over here. Q1 is a charge, okay, as is Q2. Q2 is a second charge. So any charged particle, it's usually a proton and an electron, but it does not have to be. Okay, R is going to be this distance between them. So R is the distance between those 2 charges, and then F, of course, is the force. Okay, when they're opposite, like I drew up here, the force is an attractive force, meaning it pulls them together. If I were talking about 2 electrons being near each other, that would be repulsion, so they would be going away from each other. Okay, so if Q1 and Q2 are opposite charges, plus times a minus will give us a negative force. The force is going to be negative, and that means it's attractive. If they are both negative, negative times negative is a positive, or if they're both positive, positive times positive is also a positive value. So if the force is positive, it's a repulsive force. For atomic radius, that's half the distance between the nuclei of identical atoms that are bonded together. So if I look down here, we have fluorine, this is F, chlorine, bromine, and iodine. And so when you put two of those atoms together, you can see that it's going to get bigger as we go. This is down a group. And the radius, we take it as half. So this is the radius. It's half of the distance between two identical atoms. Usually what we think about as the radius of the atom is the distance between the nucleus and the valence electrons. So that is going to be very similar to the technical definition of radius. Okay, so when I say it has a large radius, that means that it's a big atom. And if it has a small radius, like over here, that means that it's a little atom. Okay, we're going to look at the trends in atomic radius. So we're going to fill in the box below. And I would like you guys to answer right now. What happens as you go across a period? So as I'm going left to right across this period from lithium down to neon, can you see a general trend in the size of the atoms? Hopefully you can see that the atoms are going to get smaller as we go to the right. So the bigger atoms are on the left, the smaller atoms are on the right. And this is especially true if you look down here at group 4. So as you go to the right, the atoms get smaller and smaller and smaller. What happens to the radius as you go down a group of elements? Pick any group and go down, and what happens to the size of the atom? Okay, if you said that they get bigger, you are correct. The atoms get bigger as you go down. So let's talk about why. Now, the period trend is counterintuitive. It's a little confusing. Why should barium be smaller than cesium when barium has more protons and electrons in it? So if you have more protons and more electrons, why is it smaller than the one to the left of it? The answer is because in the case of cesium and barium, this is the 6s area right here of the periodic table. So cesium has 6s1 as its outer electron, and barium has 6s. It has 2 electrons out there, but they're both in the s orbital, and if I were to draw the atom with its 6 energy levels, 5 and 6, I should have picked a smaller atom, having 1 electron out here and having 2 electrons out here does not really affect the size. So what's affecting the size is the charge. With the greater charge, if I add just 1 more proton and just 1 more electron, they are more attracted to each other because of this equation up here, Coulomb's law. So what I did was I didn't really change the radius by adding an electron to the same energy level. What I changed was the number of charges, and a greater charge, positive and negative, is going to lead to a greater force. Okay, that greater force, as we move to the right, as we move left to right, the greater number, for example, fluorine has 17 positives and negatives. Boron only has 13 positives and negatives. So the greater nuclear charge pulls the electrons even closer. It has a greater force of attraction here. So as you go to the right, you're adding electrons to the same energy level. And for period 2, right here. For period 2, we're adding to the 2s and then the 2p energy level, and this is the second energy level. It's going to be the same distance from the nucleus. So we're not adding any energy levels. We're adding electrons to the same energy level 2. But what's increasing greatly is the nuclear charge, how many protons are in the nucleus. So let's sum that up. What we're going to say is that electrons are being added to the same energy level across a period. However, the greater number of protons in the nucleus, which we call the effective nuclear charge, that's how many positives are in the center, causes a greater Coulombic force. That's just a fancy way of saying force of attraction. So it causes a greater force, which pulls the electrons closer to the nucleus, and therefore the atoms get smaller as you go to the right. Now, going down a group, you guys said that it gets larger going down, and you're correct. Going down each group, the atoms get much bigger. If I compare francium down here to little lithium at the top, you can see it's much bigger. And the reason is, as you move down, every period that you move down on the periodic table, you're adding an entire energy level to the atom. So hydrogen and helium have 1 energy level. Lithium has 2 energy levels. And then if I go down, we're going to have 3 energy levels. So as you go down, you're adding a whole energy level to the atom, and that's why they get bigger going down the group. Let's answer these questions. Which atom is larger in each pair? And then we're going to put these 3 elements in order from smallest to largest. Okay, between nitrogen and neon, we're going to need to use the periodic table to look at where they're at. Nitrogen is right here, and neon is right here. What happens as you go to the right? We said they get smaller, so that means nitrogen should be a larger atom than neon. So which is larger? Nitrogen. For the second set, calcium or gallium? Calcium is here, and gallium is way over here. It's farther to the right. Calcium is closer to the left, therefore it's a bigger atom than gallium. Calcium is larger. And then we have sodium or potassium, Na or K. Which one is larger? Na is right here. K is right here. Which is the bigger atom? Well, potassium is down, so it's in the 4th period. It has 4 energy levels, and sodium only has 3. That means potassium is going to be larger. And last but not least, carbon or silicon. Carbon is right here. Carbon has, it's in the 2nd energy level. Silicon is in the 3rd energy level, so you add an energy level. So silicon is going to be the larger atom. Oops. All right, and then we need to find aluminum, sodium, and sulfur. Let's see where those are at. Aluminum is right here. Sodium is right here. And sulfur is right here. So we want to put them in order of increasing radius. So that means the smallest will be S, followed by aluminum, and then sodium is the biggest because it's the farthest to the left. Okay, so we said it was S is going to be the smallest, followed by aluminum, and sodium is the biggest. Okay, in terms of their radius. Okay, I have a silly symbol to help you guys remember the trends. If you understand the reasoning, you don't have to memorize them because you'll just use your brain to figure it out, but sometimes we need a little reminder. So as you go down a group, it's showing you that the smallest atoms are on the top and the biggest atoms are on the right. And as you go left to right, it's getting smaller. So the smallest atoms are on the top right, and actually helium is the smallest atom of them all. It's even smaller than hydrogen. Helium is the smallest, and the biggest atom would be the farthest to the left and the bottom, which is francium. Francium is largest, and this weird symbol almost looks like an R for radius, and that might help you remember the trends. So top right is going to be the smallest, bottom left is going to be the biggest for radius. All right, and most of the other trends are the opposite of that. So if you memorize radius, you can know what the ionization energy and electronegativity are. For ionization energy, we need to know what an ion is. An ion is an atom that has a positive or a negative charge to it, and that means that it has either gained or lost electrons. Ionization is any process that forms an ion, whether it's positive or negative. Ionization energy, or IE, sometimes with a little 1, is the energy required to remove one electron. Okay, so we have electrons in the energy levels. The outermost electron, the valence electron, this would be sodium. The energy required to take that electron off of the atom, that is our ionization energy. What happens to ionization energy as you go across, left to right, across the period? Okay, I'm going to look at my diagram down here. So each of these little sections that's divided off is showing us a period on the periodic table. So this is period 1, it's just hydrogen and helium. Period 2, right here, what's happening as you go left to right across that period? What about period 3, from left to right? What's going on here? Well, obviously, it's increasing. Okay, some of them are weird, yes. Like right here, this is not an increase. This actually goes down. But overall, the trend is that you're going from low to high across each period on the periodic table. Period 4 gets complicated because we have those transition metals in there. Okay, so what's going on? Let's write that down. As you go left to right, the ionization energy increases. So it increases as you go left to right. Why is it harder? Why does it require more energy to take electrons away from the atoms on the right? This has to do with Coulomb's law. So over here, these atoms, known as the noble gases, are the highest ionization energies because they are the smallest. So since they're the smallest atoms, that means, going way back to our Coulomb's law, the smallest atoms, so the lowest R value, is actually going to have the greatest. So the lower R equals a greater force of attraction. And if we're trying to take the electrons away, we have to overcome that force of attraction. So a small radius means higher ionization energy. Let's write that down. As you go across a period, the number of protons increases and the atoms get smaller. With the smaller distance and the greater nuclear charge, valence electrons are held with a stronger Coulombic force. They're just held with a tighter force. And therefore, they require more energy to remove, and that means they have a higher ionization energy. Opposite for as you go down a group of elements. So let's look down here. As you go down, this is helium, neon, argon, krypton, xenon. So as you're going down the noble gas group, you can see that the general trend in their ionization energy is to decrease. And that's because helium has 1 energy level with its 2 electrons. Neon has 2 energy levels, and then argon has 3. So as they move farther and farther from the nucleus, it's easier to take them off of the atom. Okay, let's write that down. Ionization energy has a life of its own. Sorry about that. Decreases as you go down a family. And the reason is because the atoms get larger moving down a group. The electrons are farther from the nucleus. Thus, according to Coulomb's law, they require less energy to remove. They're easier to take away because the atoms are bigger. Second ionization energy you guys might see is just the energy required to remove a second electron. So once we remove this first outer electron, if we want to remove another electron, that energy is the second ionization energy. Which group of elements has the highest ionization energy, and which group of elements has the lowest ionization energy? Let's see if you guys can answer these questions. All right, the highest ionization energy is the top of each of these periods. So these are the noble gases. I'm just going to put group 18. Which group has the lowest? So if I look, what's the lowest ionization energy in each period? It's lithium, sodium, potassium, rubidium. Those are all the alkali metals, which is going to be group 1. Okay, those have the lowest. They are the easiest to remove because they're the biggest atom in each period. Which atom has the greater ionization energy in each pair? Boron compared to carbon. We have to look at where it's at. Boron is farther to the left, so boron is here. Carbon is here. Boron is bigger, so it's going to have a lower ionization energy. And that means carbon actually has the greater ionization energy. Neon or krypton. Well, neon is right here. Krypton is down here. Krypton is a bigger atom. It's down on the periodic table. So if I look at where they're at on the periodic table, neon is in period 2 right here. Krypton is down a little ways in period 4. So krypton is bigger. It's going to have a lower ionization energy. Neon is smaller. It has the higher ionization energy. Okay, neon has the higher ionization energy. N or Ne, nitrogen or neon, which one has the greater ionization energy? N right here or Ne over here. Neon is smaller, therefore it has a larger ionization energy. It's closer to the right. So my answer is going to be neon. And last but not least, calcium or gallium. Calcium is a group 2 element. Calcium is right here. Okay, and gallium is way over here. Gallium is smaller. It's in the same period, so we know it's going to be smaller since it's closer to the right, and that means it has the higher ionization energy. All right, electronegativity is the attraction of an atom in a compound for an electron. How much does the atom pull on the electron? That's its electronegativity. So down here we can see the difference in the strength of the chlorine atom to the hydrogen atom. Chlorine has a greater pull on the electrons than hydrogen does. So we would say chlorine is more electronegative than hydrogen. It has a greater pull on the electrons. The trends down here you'll see are the same as ionization energy. As you go left to right, the electronegativity increases, and as you go down a group, the electronegativity decreases, and it's very similar reasoning. As the radius decreases, electrons get closer to the bonding atom's nucleus, and therefore they're more attracted, because the smaller they are, the greater the force, right? Let's put small r equals high force. And then as you go down, as radius increases going down, the electrons are farther from the bonding atom's nucleus. So a greater radius equals less force of attraction. So the smallest atoms actually have the greater pull on the electrons, but we have another part in play, and that's the Q, that's the charge, Q1 and Q2. So remember, this was our coulombs, ignoring the K. I'm going to use this. You guys know this symbol? This means proportional to. The force is proportional to Q1 times Q2 over R squared. So the greater the nuclear charge, you're also going to have a greater pull on the electrons. So because of those combined things, fluorine is the most electronegative element of them all. It is a crazy reactive element that will steal electrons from literally anybody you put it with, because it is the smallest radius to charge ratio. It has the greatest charge. Fluorine has 9 positive protons in the center, and also it's teeny, teeny, tiny. So it has 9 positives, and they're very small, so it has the greatest attraction for electrons of all the elements. Electron affinity is very similar to electronegativity, except instead of it being in a tug-of-war in a compound, this is just you have an atom floating around. So you have just this, let's say it's hydrogen floating around, and how much does it want to gain an electron? Okay, so that how much does it want to gain an electron is very similar to the pull that it has on the electron. So you're going to see the exact same trends, and we're not going to write them down. For ionic radii, we need to remember that cations are positive. Cations are positive. Let's give them a little positive nose there. Okay. And anions are negative. The metal atoms tend to form cations. They're positive. So all the elements on the left of the periodic table tend to be positive. Nonmetals tend to form anions, which are negative. So the right side of the periodic table tends to form negatives. Why is that? And here is a summary of that. These have 1 or 2 valence electrons. So group 1 and group 2 have 1, 2. This one has 3 valence electrons. And remember, to have low energy, it wants 8. So these noble gases over here with 8 valence electrons, they're more happy than all the others, which means they're more stable. They're lower in energy. So they all want to get to this 8 valence electrons. Well, group 1 and 2 are very far from having 8. So they are going to give up their electrons and become positively charged. Same thing with group 13. It's going to form a +3 charge. It's going to lose its 3 electrons. Underneath those outermost electrons, they have a full shell. So they're going to lose the outer electrons. Over here, these nonmetals tend to form negative because nitrogen, for example, has 5 valence electrons. I'm going to put VE for valence electrons. And it's only 3 away from having 8. So nitrogen is going to do what it can to find an extra 3 electrons and become a full octet. So when it has its 8 electrons, it becomes more stable. Oxygen's group has 6 valence electrons. So it wants to gain 2 to have that full octet. So it's going to be -2. The halogens are almost always -1 because they are just 1 electron short of having their full octet. So they're going to do what they can to gain an electron and have the full S and P orbitals. And then the noble gases here. These guys already have their full octet. So they don't really want to form any kind of charge. They're going to have a neutral, 0 charge because they don't want to gain or lose anything. They're already happy. They're already stable. All right. So the elements on the left tend to lose electrons and become positive. That's what we saw up here. The atoms on the right tend to gain electrons, and that means they become negatively charged. As you go down, it's the same trend. So even if these were all charged, as you go down a group, the atoms or the ions are still going to get larger as you go down. Okay, and what I want you guys to know is that cations, the positives, are almost half the size. So they shrink, just losing 1 electron from here to here. Lithium has lost 1 minus 1 electron. Look at how much it shrunk from 152 picometers down to 60 picometers. So it's much, much, much smaller. Same thing with sodium. When it loses just 1 valence electron, it decreases by about half its size. When an atom gains an electron, it becomes, so this is from here to here, we're adding +1 electron. It doubles in size roughly. This is more than doubles actually. This is about doubles from here to here. So anions are almost twice the size of their neutral atom. Okay, so when they become positive, they get much, much, much smaller. +2 is an even larger change in size. And when they become negative, they blow up to twice their size. And that's because you have extra electrons over here. So these repel each other even more. So they push each other away, farther away. When you have an unbalanced positive and negative, the 1 less electron means the protons now outnumber the electrons and they pull them in even closer. So that's why you see such a big difference. And last but not least, the charge clock is just to help you remember the charges on the groups. So if we have group 18 here, group 14, 13, this is 1 and 2, this is the S block. And then we have 16, 17, 15, trying to spread them out evenly. So in these this is the group number. What is the charge in that group? 18 has no charge. They don't want to gain or lose any. Group 1 has a +1 charge. Group 2 has a +2 charge. Group 13 had a +3 charge. And then the halogens had a -1. The group 16 oxygens group was -2. Group 15 nitrogens group, -3. And guess what? These can be plus or -4, but what they really do is share electrons. So you're going to see covalent. You're not going to really see any kind of charge on carbon's group. It always wants to form a covalent bond. Okay, unless you have calcium carbide, which is highly explosive and super reactive. You guys can look that up. There's some cool videos. All right, that is it for today, and I hope you guys have a wonderful day.